All right. Boy, getting COVID flashbacks a little bit here on Zoom, but here we are because I don't do this very often. Welcome everyone who's here and on time. Thanks for being here. We're excited to go over part two of the Super Six. My name's Jared Dirksen, AP Stats teacher in Southern California, and with me is my good friend and colleague DeAnna McDonald, who teaches at University of Arizona. Is that right? University,
And
not,
totally don't say the other name.
I
Yes,
will not
University of
say the
Arizona.
university. We will not talk about those who should not be named.
Yes. And
And
they are devils, both literally and figuratively.
I love it. We have a high school up the street that shall not be named. So yes.
Okay.
I teach at a high school. DeAnna taught at a high school for a long time. We co-author Five Steps to a Five together. I worked on Stats Modeling the World a bunch. DeAnna's worked on the Flamingo book a bunch. Yeah, we've done a ton of things. We've graded AP exams for many hours of our day. DeAnna's helped write scoring guidelines for those exams. So here we are, quite fluent in AP stats, and we hope to give you guys some great tips and pointers for this review. You probably already know this, but just in brief, the Super Six are six old AP questions from 2022 and 2023. I took these six questions. We kept the original questions. I kept the original questions and then kept adding extra parts until we covered everything in the course up to inference. And we're going to throw in a few extra inference questions today. But the goal of this material is to review probably what was your whole first semester for many of you. All the topics of first semester. So that said, let's dive in. We're going to start with question number four. Number four on the Super Six for the last 3 years in a row now. The first question on the AP exam has been an exploring data question that can be center shape and spread with a quantitative variable. That could be regression. And then question number two has been where you get to write your brains out. And so this was a question number two, and it was about an experiment, as we see right off in the first sentence. We had an experiment 2 years, or no, was this, I think this was last year. This was 2023 experiment. We had a survey 2 years ago. So I'm predicting number two will be a survey this year for whatever that prediction is worth, which is not much. So anyway, we have an experiment on a new drug to treat acne, and we have 36 pairs of identical twins. Isn't that convenient? And all the AP Psych people are excited about twins studies. Each person has acne, and each person will receive either the new drug or their placebo. And then after the experiment, which will run for 2 weeks, we'll rate their improvement on a scale of 0 to 100. So your first question here, part A, was to identify the treatments, the experimental units, and the response variable. So the treatments in this case would be the new drug or the placebo. And that is what that is the treatment that's being given to the experimental units. And experimental units is sometimes a weird vocabulary word for you guys, but you could also think of that as subjects. You should be aware, you very well could get a question about an experiment on non-humans, maybe an experiment on testing cell phones to see if they can endure, drops or something. And then the cell phones would be the experimental units. So we often call our experimental unit subjects when they're humans, which is just nice. So the experimental units are the 72 people who receive these treatments. You should be aware that there were lots of ways to say this correctly, that we had 72 people, that we had 36 twins, 36 pairs of people. If you said there were 36 experimental units instead of 72, you would not get full credit because there are 72. So if you said 36 twins or 36 pairs, that would be fine. But it wasn't okay to say 36 experimental units because we did have 72 different individuals getting the treatments. The response variable, that's what we're measuring at the end of the experiment. And that's in our last line there. We're going to evaluate the improvement of acne severity on a scale of 0 to 100. So this is really common, part A for an experiment, treatments, experimental units, response variable, and we're going to hit some of the other vocabulary as we keep going here, but that's a really common way to start an experiment. Now we get to, I think one of the hardest questions that can be asked, just period, which is a why kind of question that makes sense intuitively, but is hard to explain. And so we know that the acne severity differs from one twin pair to another. But what is the statistical advantage of using a match pairs design where the twins are paired rather than using a completely randomized design? Reminder, completely randomized design is when we just take our subjects, we put them all in one bucket, we stir them up, and then we randomly sort them into the treatment groups with no matching, no blocking, no sorting going on in any way. So this feels so obvious, right? Like, oh, this is great. I've got these twins. And then comparing the treatment on twins is better than just two random groups of people. But why? All right, so let's talk about why. And we need to be as statistical as we can here as we dive in. So improvement on scores will vary due to many factors, right? You've talked about this all year long in statistics, that there's all these variables running around. We have your initial acne severity, what kind of treatment you receive, diet, genetics, all these things, maybe your face washing habits, all these things that are going to affect this. But twins are going to be very similar in initial acne severity. They're also going to be similar genetically, and maybe there's other ways that you might talk here on this second paragraph about how the twins would be similar. Therefore, the match pairs design will provide a more precise estimate of the difference of improvement for the new drug compared to the placebo and make it easier to find convincing evidence that the new drug is better, if it really is better. Maybe a shorthand way of saying this is you can better see the effect of the treatment. Since the twins are very similar with similar acne, similar genetics, similar habits, they're similar in all these ways that affect how your acne might improve or not improve. Then their similarity will help us isolate the effect of the treatment. That's a phrase I'm kind of fond of for problems like this. Isolate the effect of the treatment so that I can see whether or not the drug really affected the change. So yeah, that's a tough one. My students were doing that just the other day, and it's hard to describe. So something to just keep working on and thinking about. All right. Now we have to describe how the treatments can be randomly assigned to people using the match pairs design. And so when you're describing how treatments are randomly assigned, this is where you really have to go step by step and kind of over explain things, how we're going to actually do the random assignment. And so one option would be to label them twin A and twin B, and then we would toss a coin, and twin A gets the placebo and twin B gets the active drug. If the coin lands on tails, then twin A gets the active drug and twin B gets the placebo. Coin flipping for match pairs works out really nicely, works out really in a straightforward way. Or maybe you label them and then you use a random number generator and you generate an integer from 1 to 2. And then whatever number is selected, that person would get the placebo, and the person that's not selected would get the number selected. And we're just going to repeat that over and over again for all the twins. Or maybe you want to use, slips of paper in a hat or note cards. And so you take your cards and you label them and you shuffle them. and the twin who gets card A gets the drug, or maybe you put drug and placebo on the cards and you shuffle them, and then, the twins come up and they pull out cards. Last year, in recent memory, it was very important that when you're pulling slips of paper out of a hat, that you not only shuffle the slips of paper in a hat, but that you pull them out without replacement. So I would encourage you to do that. When you're talking about a random number generator, and if you're doing lots of random numbers, you want to talk about selecting unique, non-repeating random numbers. So your thoroughness is rewarded on these rubrics for sure. All right. That is the end of the original AP question, just for your information. It's pretty common to have, again, the last 3 years, we've had a survey or an experiment on question number 2, and it's had 3 parts, A, B, C, and lots of writing when you get to question number 2. The order might not stay that way. It's possible they could mix it up, but we're on a 3-year, we're on a 3-year streak here. So now we've got the extra questions that I wrote. Suppose that instead of 36 twins, we had 100 volunteers, and that 60 of the volunteers were teenagers and the rest were middle-aged. Why would a block design be appropriate, and how would this design be implemented? And so we have a why question here. Why do we use block design? And you've maybe memorized blocking reduces variation, but let's explain that thoroughly. Teenagers probably have different habits, hormones, etc., that affects acne differently than middle-aged people, and this would create variability. So we're reducing the variability by blocking the variability in the response variable. Experiments are always about isolating the effect on that response variable. So it's important to get that in there. And then how would this design be implemented? The idea of a block design is that we would randomly assign half of the individuals to each, within each block, to the drug and the others to the placebo. And again, you might be asked to define that in a step-by-step way, again, with names in a hat or a random number generator. Notice that we didn't talk about comparing the teens to the middle-aged volunteers. And that's something that you really shouldn't talk about. It's kind of a side benefit of blocking, but it's not what blocking is about, especially strictly according to kind of our AP stats guidelines. Blocking is to reduce the variability that we know exists in our subjects in some way with respect to the response variable. Certainly, if you're a researcher and at the end, maybe you do all sorts of different comparisons. Did my drug work better with older, younger people, with gender differences? Who knows? A ton of possibilities. But you shouldn't talk about that comparison. You shouldn't talk about comparing blocks when you're talking about block design. That has been considered off topic on the rubrics. All right. Blocking, and here we have kind of the final why. Blocking by age would evenly distribute the age groups to the treatments and reduce the source of variation. Okay, so moving from blocking, moving on to double blind. And students sometimes get confused by double blind because they feel like someone has to know what's going on. I always picture the movie Frankenstein with Igor, the lab assistant, setting up the experiments in the back of the room, or maybe Young Frankenstein, depending on your taste. But, but in this case, it's very easy to grab to have a placebo and make it look just like the medication and have it labeled by an assistant. And then neither the subjects nor the evaluators need to know what's in those bottles. And so that's easy to do. When can't you do double blind, you might wonder? Well, if I ask you to do something where it's kind of obvious what you're doing, like maybe I say, well, we're going to do a weight loss experiment, and some of you are going to exercise and some of you are going to, eat only celery for a week. Well, then I cannot hide from you what it is you're doing. That's would be an example of when we can't do double blinding. Another experimental design word is replication. Do you remember what replication is? Replication is something you talk about in your science classes, and it just means that we've got a bunch of people in every treatment group. More than one person receives each treatment. Um, if that feels shallow, you are right. A lot of you will go off to college and take stat 2 and learn how to do power studies and figure out what sample size you need, how many subjects you need to measure what you want to measure. But that just goes a little bit outside of AP stats. There was a question one year where they only did each they did each treatment just one time to one plot of land, and they asked about replication, and the answer was no, there wasn't replication because this hitch was only used once on each plot of land. All right, moving on. Another vocabulary word here. Factor. What is the factor and how many levels are there? So the drug is the factor. The factor is the explanatory variable that we are manipulating, and we were just manipulating it in two ways, with the real medication and the placebo. So pretty straightforward question there, as long as you remember what a factor is. When there's only one factor, the factor and the treatments end up being exactly the same thing. So we have two treatments, we have a factor at two levels. What does the phrase statistically significant mean? And that's something that maybe you talked about early in the year very loosely, and now you've run a million hypothesis tests, so you feel really smart about that. Statistically significant means a bigger difference than would happen by chance. And now you've learned how to measure chance variation. You've learned how to run a hypothesis test and say, oh, this is very unlikely to happen by chance. It happens, less than 5% of the time. So that's the definition of statistically significant. Part 2 here. We should notice the word caused. Can the researcher conclude that the medication caused the improvement? And as soon as you see the word cause, your alarm bells should go off. That's a hugely important word to us, right? And we immediately start thinking, do we have an experiment? Do we have an observational study? Do we have a survey? Yes, this is an experiment, so we can make a causal conclusion. If we get a small p-value at the end of this experiment, we'll say, yep, the new drug actually caused a difference. Now, you you still want to be careful. I want to encourage you to always be careful. Sometimes students say, the medication worked, period. No, we finish a hypothesis test with, I found statistically significant evidence, and maybe it's very, very strong. Maybe your p-value is super small. So you say, I found super strong statistically significant evidence that the medication caused an improvement in people like my subjects, period. Stop talking. Sometimes students like to add something like, so we know it works. No, we have evidence that it works. And sometimes you guys just kind of can't contain yourself there. You've probably memorized, I'm sure you memorized by now, my p-value is less than alpha, so I reject the null. I found evidence that. So we say we found evidence. We say that evidence gives us belief that the treatment caused a change. And then we stop. All right. Who can this conclusion be applied to? And the answer is it can be applied to people similar to our volunteers. And if you haven't done an FRQ recently with your teacher where you've noticed this super careful wording, is there statistically significant evidence that for people like my volunteers? Go looking for a question like that. It's not hard to find. So we want to be very careful with our conclusions. If we're not taking a random sample, if we're sampling on volunteers, then my conclusion applies to people like my volunteers. And that's one of the bummers about experiments. I remember when I was in college taking stats, they figured out that baby aspirin helped prevent heart attacks. But the first experiment ever done on that was done only on a bunch of doctors. And then they were like, oh, I think male, is that what you're saying? I think, yeah, it was all male doctors. And it's like, okay, so then, and they were super excited because the results were, it was not a small change, right? And some of you, your dad, your grandpa, whatever, me, take a baby aspirin. But and but yeah, so then they work and they expand the scope of the conclusions. So, all right. Um, Describe why a placebo needs to be used as a form of control. This is another one of those why questions. So challenging to think about, to practice. It's hard to know. Good news, you're probably only going to get one or two on the AP test. It's not going to stop you from passing the exam. But boy, these are always some of the tough rubric points. So why? Well, placebo serves as a baseline for comparison. And by the way, you could hold on to that phrase right there, like for a control group too. Like sometimes when we run an experiment, we monitor some people who just aren't getting any treatment at all. Why? As a baseline for comparison. So we can just see what's naturally happening with the population. So the volunteers know they're going to have their acne severity evaluated. So they might be more conscientious. They might wash their face more, which, was a good habit, right? And so then that might cause some improvement. But the placebo group will help the researcher see if the drug itself made a difference more than just the placebo, more than just, hey, I'm part of this experiment. One of the big problems with experiments that we probably don't talk about a lot in AP stats is that it's hard to make them realistic. So there's some fascinating research right now about all sorts of research about humans and social media apps and our phones, right? This is a hot topic. But when you try and run an experiment and you say, no phones or no Instagram for a month, it's just weird because humans they know they're being experimented on, and it's a tough thing to do. So anyway, moving on. All right, I think that was nope, part J. Yeah, part of why I call these the super six is because they get super long. So here we are, part J. And this was a added bonus question I added for inference. So if we want to run an inference procedure on the original twins experiment, what would be the appropriate choice? And I really want to pause here. In my classroom, I call this name that test. Pick the right inference procedure for this process. So again, if you all the way back up to part B, we have these pairs of twins. We're going to experiment on them. Half the twins are going to get the placebo, half the twins are going to get the new drug. What is the inference procedure for this experiment? And that would be a match pairs t-test for the mean difference. Now, I typed out the fullest name for a t-test I could think. You probably don't need all those words to name it properly. You could probably just say a match pairs t-test or maybe a t-test for a mean difference. But there's the full name. All right. Let me ask you this. What if we wanted to run an inference procedure on a completely randomized design? What would be the appropriate choice? So again, reminder, completely randomized design mean I take my subjects, maybe I have 200 subjects, and I just put all their names in a hat, and I randomly pull out 100 names. You guys get the drug, randomly pull out 100 names, you get the placebo. Does that change what I'm going to do? I still probably have the same number of people doing both the placebo and the drug. Can I still run a match pairs? No, we can't. We're going to do a two mean t-test for the difference of two means because now my subjects are not going to be paired in any meaningful way. And as many of you have figured out by now, um, figuring out the difference between match pairs and two mean is one of the harder things to figure out because in both cases you have two data sets, you have two means, you have two standard deviations. Um, and if the groups are the same size, well then gosh, it sure feels like I'm not sure what to do. Um, and so here's a little a pro tip for you. I was working with my students and we were looking at 2018 number 4, which was two mean, and we were looking at 2014 number 5, which was match pairs. And I would encourage you to go look at those two problems and contrast them. Now the two mean one was extra helpful because the sample sizes were not the same size. I think one group was 100 and one group was 110. So then you really know that you're not in match pairs land. But the 2014 problem, and there's plenty of match pairs examples in the history of AP stats, but it's just kind of a lovely little problem because the matching was really clear throughout the problem. And they told you the mean difference and the standard deviation of the differences. And the data was paired up throughout the presentation of the data. So I would encourage you to look at those and keep practicing that. I feel badly when I say it, but when students say, how do I tell the difference between match pairs and two mean? The best answer is, well, is the data matched? That's that's the answer. The other pro tip I can give you is that I believe every time match pairs has been on the AP test, the data has been presented with 3 rows, not 2 rows. That is a row for like one twin, a row for another twin, and then like the labels on the twins, twin pair 1, twin pair 2, or twin pair A and twin pair B. So the AP test has gone out of their way to say, here's how the data is matched. And again, if you flip through a couple of old examples, I'm sure your teacher can give you examples, or you can Google your way to match pairs on the AP test. You will see that matching throughout. So, and the other good news I have for you is if you do mix those up, you're not going to get a 0. You can still usually rescue a 2 out of 4 on the rubric if you mix up match pairs and two mean, because they are both at least somewhat appropriate, right? It's quantitative data, it's means, it's standard deviations. If you take a chi-squared problem and treat it like means, you're not going to get any points. Sorry, that's no soup for you when you mix up categorical and quantitative data. So, yep. And if you're not playing Name That Test a bunch with your teacher, there's some great websites for that. Khan Academy has packages of like 7 FRQs in a package where you can go through and play Name That Test over and over and over again. So highly recommended. My friend anyway, my buddy a good guy wrote some good problems on Khan Academy for Name That Test. Josh, I think. What gosh, why am I forgetting? Anyway, do you know DeAnna? Is it Josh? You don't know? Oh, yeah. Anyway. All right, on to question number 5. When we are now in probability land, so as I keep reminding you about how the AP test might be structured, question number 1, exploring data. Question number 2, explaining data collection, a survey or an experiment. Question number 3 has been probability. And then question number 4 has been the inference question. So again, I cannot promise. I have friends who have graded some of the like international exams, and they've told me that the order has been different. But the US exam for the last 3 years has followed this order. So we have shampoo bottles and we have a normal distribution. Oh, that's always an exciting word to read. And we've got a mean of 0.6, which right there we're like, oh, I've got a mu, and we've got a standard deviation of 0.04. Oh, I've got a sigma. And so then we've got a random variable that is how much shampoo in liters is inserted into the bottle by the filling machine. Yep. And people pay attention to this. True story, the state of California got sued because Heinz ketchup bottles were underfilled, and Heinz ketchup had to pay like $500,000 to the state of California. So Someone actually keeps track of this stuff. So a bottle is underfilled if it has less than 0.5 liters of shampoo. What's the probability that a randomly selected bottle of shampoo will be underfilled? Show your work. All right. So oftentimes your probability question starts out with a nice, straightforward, normal question that hopefully you are really good at. And if you're not a total math geek, you maybe hated some parts of probability, like, binomials and the Pythagorean theorem of probability and yada, yada, which we're going to review all of that. But man, a normal problem is a nice way to, start out strong. So we've got a mean, we've got a standard deviation. We're doing less than 0.5. You're going to run your normal CDF on your TI, whatever, or maybe your Casio, or maybe your NumWorks. And you're going to get 0.0062. You can write that as a decimal. You can write that as a percent. You could write 0.62%. That would be fine. And maybe you draw and label and shade a normal curve. That would be lovely. Let's make sure you all know what you need to do to get full credit on this problem, okay? How do you show your work? You have to indicate that you're using the normal button on your calculator. You could write the word normal CDF there, that counts. You could draw the normal curve. If you write the z-score formula and use the letter Z, even though we use Z for more than just a normal distribution, that counts. So you have to get the normal there somehow. You have to have mu and sigma labeled. So I labeled mu and sigma in the parentheses there with the calculator command. That's one way to do it. It's also labeled on the line where it says given, mu equals, sigma equals, so I labeled them twice. Notice on the normal curve, I cut and pasted that out of one of my favorite software packages. It doesn't have sigma labeled, so that would be, you would not get, I always have my students write sigma on top of the normal curve like a hat, where it just write sigma equals 0.04 at the top. So you need mu and sigma. You need the boundary and direction. So the boundary is 0.5 and the direction is less than or equal to, doesn't matter. So on the normal curve, 0.5 is marked and shaded. So that's boundary and direction. Writing A is less than 0.5, boundary and direction. Writing lower bound and upper bound, and -999 and 0.5, boundary and direction. Sometimes you guys write your answers in words, and that's another way that oftentimes you communicate the boundary and direction, because you say the probability that the bottle is less than 0.5, and then you say less than 0.5, so you're getting the boundary and direction. I graded a problem one summer with melons, and a lot of students, they'd either not write a less than anywhere, and they wouldn't shade the normal curve anywhere, but then when they wrote the answer in a sentence, they would say the percentage of melons that are less than this, and then they'd have the boundary and direction. So, all right. Hopefully you practice that lots of times with your teacher by now. Now we get to part B. After the bottles are filled, they are placed in boxes of 10 bottles per box. And then they're shipped off. And so they're going to randomly select bottles from the crate, and if 2 or more are underfilled, the crate will be rejected. All right. So now we've got question B. They're interested in the probability that a crate will be rejected. And we're going to assume that we have independent observations. That should be giving you a hint what we're going to be doing right there. And now we're asked to define a random variable. This question showed up, I think, 3 years ago for the first time, and it showed up 2 years ago, and then it didn't show up last year. Define a random variable. This question is not in your books very much, if at all. But we'll see if it happens again this year. But what you're supposed to figure out is that this is a random variable that we're going to call X, where we're going to count the number of underfilled bottles. And then when we're counting the number of successes out of a fixed number of trials, that's binomial. N is 10. We figured out the probability of a success, which is underfilled, as 0.0062. And so we've got a binomial situation going on here. So again, you may not have defined a random variable very often in your class, but here it is. You could do this maybe with a geometric variable too. Like, what's the probability? How long will it take until you get your first underfilled bottle? And then you'd have to define something geometric. You wouldn't have an N, then you would just have a P. They haven't done that yet on the AP test, but they could. So there's the definition of the random variable. Now we want to figure out the probability of rejection, part two, B2. So if two or more are underfilled, then that's going to end up with the rejection. So we want to figure out the probability that X is two or more. We have this binomial variable, and maybe, here's where reading a whole FRQ before you do it, and I know that's so hard to do on the AP test. Man, that's hard to do. You guys just want to work through it in order. You read the whole thing through. You read A, you're like, okay, normal problem, that's going to be easy. You read B, maybe B1, like defining a variable thing. And then you read B2, wait, that sounds binomial. Maybe B2 helps you figure out how to do B1. And so now your calculators, most of your calculators won't do greater than or equal to for a binomial. You're going to use your binomial CDF command, and you're going to do less than or equal to. And then you're going to do 1 minus that. And so I don't know if anyone out there is using the NumWorks calculator. If you're using a NumWorks, they will do greater than or equal to. And for any teachers listening, I had about 30 kids out of my 100 kids buy NumWorks this year. And oh my gosh, it has never been easier. It's never been easier to teach the calculator. Like, I just point them to the right menu and they can read from there to figure it out. But that calculator is beautiful. Seriously. I'm not paid. I'm just convinced that thing is, it will help your students understand, because not only will it do greater than or equal to for a binomial problem, it gives them a little histogram, a little line graph, and shows them highlighted all the parts. You can go see the free emulator online. And honestly, when my kids forget their calculator, they just pull up the app on their phone and they do it on their phone, which obviously doesn't work for test days, and yes, it's AP approved. So anyway, end of commercial, but yeah. I literally just say, hey, NumWorks, go do this. And then I have to teach my Casios and TIs how to use their calculator. It's pretty stark, the difference. All right. Now we get to the last part of the original question, which is that they're maybe thinking about switching to a machine that has a mean of 0.56 and a standard deviation of 0.03. And we're wondering if this is better. Now, you might almost be tempted at this point, like, oh, am I supposed to do something inference-wise, or what's going on here? But you're in probability land, right? You've done a normal probability, you've done a binomial probability. And so don't be surprised that you will use a probability answer to answer just kind of a common sense question. And we're going to take this new mean and this new standard deviation, and we're going to run another normal CDF, and we're going to get a probability of 2.28%. Okay. Is it 2.28% is a bigger percentage than the 0.006 that we got a minute ago. And so seems like they should keep going with the original one, that the original one, that this new one would result in more rejected shipments. And so again, don't be scared, especially on the probability question, to just use your probability to answer, yes, this seems likely, or this seems unlikely. This seems better than this. This is more likely than that. So, yep. All right. End of the original problem. Now we're going to dive into more probability. Let's talk about the empirical rule. Do you remember what the empirical rule is? So that's the old 68, 95, 99.7 rule. And so I don't know that this would make a great AP question, probably not, but just reminding you, 68% plus or minus 1 standard deviation, 95% plus or minus 2 standard deviations. 99.7%, 3 standard deviations. And if you're taking AP Psych, you've got this super memorized and that's all you're going to use. I will say, if you're doing a problem on the AP exam and you get a Z-score of exactly 1 or 2 or 3 or -1 or -2 or -3, and you're thinking, can I just use I got a Z-score of 2, so it's the top, 97.5% or whatever. Can I use that? You usually can. In fact, I would say you always can. Whenever a question has been written, and DeAnna, you can correct me if I'm wrong, but I feel like anytime the Z-score has been exactly 1, 2, or 3, plus or minus, you could use the empirical rule instead of take the time to get the exact value out of your calculator.
That is correct, but
Oh boy.
only if the distribution is approximately normal to begin with. So you can't go backwards and say, well, I got a Z-score, so I'm going to apply the empirical rule.
Yep.
Which
Yep.
is
And that's a really good reminder. You should only press the normal button on your calculator when the problem says it's normal or when you're applying the central limit theorem. I always tell my students at the beginning of the year, you can only press the normal button on your calculator when the problem says it's normal or when I teach you something later. And then we learn the central limit theorem and it's like, okay, now we have this new path to pressing the normal button. And for goodness sakes, please never describe a histogram or a dot plot as approximately normal. Just don't do it unless you're appealing to the central limit theorem, unless it's like a simulation and you've got like a big pile of sample means and the sample size is bigger than 30, then sure. But normal is not a shape word. It's not in your center shape and spread vocabulary. It's just not. Your center shape and spread vocabulary is uniform, bimodal, symmetrical, skewed left, skewed right. That's it. So anyway, all right, enough cautions. All right. Now we've got how many liters of shampoo are in the 6% most overfilled bottles. So now we're working on an inverse normal question. And again, you should mark, label, and shade a normal distribution. And the rubrics will be the same. Are you going to tell me it's normal? Are you going to communicate the mean and standard deviation? Are you going to mark your boundary and direction? And sometimes you guys get mixed up if you're doing left and right on your calculator. So yeah. And if you're using table A, that's fine. I'm sorry if you're using table A, but it's an okay tool. But all right, moving on from that. Find a Z-score and interpret that value in context. And by now, Z-scores should just feel really kind of pedestrian. And boy, you've done them a million times. Find a Z-score. Reminder, the Z-score formula is on your formula sheet. Your formula sheet says standardized test statistic equals statistic minus parameter. So it can remind you about that. Reminder, if you're above the mean, you're positive. If you're below the mean, you're negative. And then it's just standard deviations above the mean. So not a super frequent FRQ, but you're going to see that language in there somewhere. And think how much you've grown. At the beginning of the year, standard deviation was this weird thing. And now we write this sentence that, this value is 1.25 standard deviations above the mean. And you're just like, yeah, yep. So you've learned so much. All right, part G. Suppose you want no more than 2% to be underfilled. What standard deviation satisfies this requirement? Now, depending on your calculator skills, there might be a way to get around. In fact, I want to say on a NumWorks calculator, there's a way to plug this in and it will back solve for the standard deviation for you. but I really leaned into doing algebra on this problem. So we need a z-score for the bottom 2% is what we need. And you should definitely know how to put your calculator in z-score mode. That would be the standard normal distribution. I'm going to pause for a second. Do you know what to use in your calculator to put it in z-score mode, to put it in standard normal distribution? So I hope you said mean of 0 and standard deviation of 1. And some of your calculators default back to that all the time, and some of them don't. But if you use your inverse normal for that bottom 2%, you're going to get a z-score of negative 2.04554. And then you're going to write a z-score formula. We know the cutoff for underfilling is at 0.5. And we're comparing that and we're keeping the mean at 0.6. And again, we got that negative z-score from either inverse normal or the z-table. And maybe, maybe table A is a fast way to get that for you. That's great. And then we do some algebra, do a little cross multiplying. Remember, sigma's on the denominator, so multiply by it, and you're going to divide by the z-score. Okay. Word of fair warning, that problem is written to remind you that the AP test, you're going to get a straightforward normal question, but you're probably going to get a normal question, maybe somewhere in the MCQs where you have to apply what you know about the normal distribution in a slightly different way. Solving for the mean or solving for the standard deviation is one of the ways that question shows up. So. All right, part H. We're going to go back to part A. We're going to grab that original information and we're going to say, what's the probability that 4 randomly chosen bottles have a mean amount that is 0.615 liters or more? And my goodness, I did this problem with my students, and then we did a different FRQ the other day, and they promptly forgot what to do here. The word mean is the crucial word there. What do you know about a mean? If you've got your formula sheet handy, could you grab your formula sheet? And which part of your formula sheet would help you with this question? There's a lot of means on there. There's a lot of formulas. And again, the original stem is that we have a mean of 0.6 and a standard deviation of 0.04. We're actually talking about a sampling distribution here. So do you know what sampling distribution we're talking about? And we've got a sample of size 4, and we're talking about the mean of a sample of size 4. So the big trick here on this problem is to remember that sigma gets divided by the square root of n. And we can't use the standard deviation of 0.04. We're going to use a standard deviation of 0.02. Once we figure that out, we just know to run a normal problem. So this is a sampling distribution question. And we run the normal calculation. And again, a lot of you probably show a z-score calculation. That's a great way to show work. If you write that whole thing right there, you've actually shown all the work you need to show, because you have the boundary, the direction, z is normal, you have mu and sigma, so you've got the whole thing. So should I tell them the just draw the darn picture story, DeAnna? Isn't that a great story? DeAnna had a student one year, he'd never draw the picture, and she said, just draw the darn picture. And on the day of the AP exam, the student drew the darn picture, and he wrote a note on the problem. See, Mrs. McDonald, I drew the darn picture. And someone who knows Mrs. McDonald graded that paper. And did you actually get to see the paper, or did they just come and tell you the student wrote?
No, they came over to where I was scoring booklets and said, one of your students said to tell you that he drew the darn picture. I said, oh, thanks. I know who that is.
That's fantastic. All right. Just another way to show work here. And you could draw a label and shade a normal curve. You could just draw the darn picture. But the key thing to remember here is that we have a standard, we have a mean, a sample of size 4, and we have a mean. All right. Part J, what assumptions are required for a sampling distribution? And someone asked before we started about checking conditions. You could be asked about this question. Describe, how do you justify, how do you know that the sampling distribution of the sample mean is what you say it is? And so we have the 10% rule. We have randomness. We have the sample size condition. The problem stated that the sample was random. It's certainly reasonable that we have, more than that the population is more than 40. And the stem of the problem told us that the problem was normal. And you're used to checking normality lots of different ways. You're used to checking n times p and n times 1 minus p greater than 10, or n is greater than 30, or making a graph. Don't forget, the problem might tell you, hey, the population is normal. So then you should still say, hey, since the population is normal, I know that x bar is approximately normal. But that is a way to take care of that. So what if we crank the sample size up to a sample size of 30? And so the only thing that changes in the problem is the standard deviation. And so now we're going to divide by the square root of 30, and we're going to get a much smaller standard deviation. The shape is still normal, and we get a much smaller probability than we had before. I want to pause here to tell you a little story. And if you're taking notes, you have some time to take some notes while I take the story. Why do means vary less than individuals? Why did the standard deviation get so much smaller? Why am I dividing by the square root of n? Suppose I told you that this morning I was out on my campus and I was talking to a student, and the student I was talking to was 6'2". Are you very surprised? Well, high school campus, 17-year-old kid, 6'2", point guard on the basketball team, whatever. Sure. Yeah. Not surprising. Okay. Now suppose I told you 2 days ago I was out on campus in the morning and I was talking to 4 students and their average height was 6'2". Are you surprised? Well, then, yeah, you'd be kind of more surprised. 4 students, an average height of 6 foot, like these are tall kids. Like maybe you're talking to the, 4 of the basketball players, or 4 kids in the Dutch pride group on campus, or, you're talking to 4 unusually tall students. What if I told you I was talking to 30 students and that they had an average height of 6'2"? Well, now you would be aghast, right? You would be amazed. Like, what kind of high school do you teach at? Where do you find 30 students who average 6'2"? Um, and I do have a Dutch friend at school, and he's 6'4". They're the tallest people group in the world, I believe. But means vary less than individuals, right? One person being 6'2", not that surprising. 2 or 3 people averaging 6'2", not that surprising. 30 people averaging 6'2", that is super surprising. So means vary less than individuals, right? Our intuition tells us that. And where we get to AP stats land is how much less do means vary than individuals? Answer, divide by the square root of the sample size. That's where we really get to AP stats land. So, all right, plunging on ahead. I hope that's helpful. So now question, and this is, what's the big difference? What if the population was skewed, and how would that affect samples of size 4 and samples of size 30? And this is where hopefully by now you've really memorized that when my sample size is small, that if my population is skewed, then my sample mean will be distributed similarly to the population, especially for skewed distributions. So my sample mean would be skewed and it wouldn't be approximately normal. Whereas, thanks to the central limit theorem, the central limit theorem says that when 30, a nice big sample size, then the mean is approximately normal. So that would not change the answer. So short version, I couldn't do question H, but I can still do question K. And by the way, if you're bothered that we're exactly 30, 30 is a rough rule of thumb, people. If the AP test wants you to invoke the central limit theorem, you're going to probably have a sample size of 40 or more. They're not going to kind of leave you on the fence. Likewise with n times p and n times 1 minus p greater than 10. If they want you to assume normality, those values will both be bigger than 10 for sure. But it's not like at 10, it doesn't work, and at 10.1, it does work. I mean, this is a continuum. But anyway, test questions will be clear. All right. Moving on to our last question, question number 6 of the Super 6. And this is another probability question. This was last year's probability question. This was number 3 on last year's exam. And so we have these bath fizzies, and there's a cash prize. Twitter was hilarious with the bath fizzies. So many bath memes, bath bubble bath themes on Twitter right after the exam. And then we get this given distribution. We get something that looks like this. Okay. And as soon as you see a table like that, there should be one thing that comes right to the top of your brain. And that is expected value. There's a decent chance you'll get a table like this on an MCQ and you're going to crank out the expected value. And yeah, we're not going to get to that to part C, but it's as soon as you see a table with some sort of quantitative variable and then the probabilities for each of those quantitative variables, you should just be ready to go with expected value. So part A, what proportion of bath fizzies contain the $1 prize? And we see that the table is made so that we have all the probabilities that we need except one. And hopefully you remember that then this table has to add up to 100%. And so you just do 1 minus the probabilities that you've got, and you get that we have a 68% probability for the $1 prize. So, on the day of the AP test, if you're missing some values and have to figure out some values, definitely just write them in there. So now we've got the whole probability table. So, all right. And now we've got the next question about that part 2 was what proportion of bath fizzies contain at least $10? So we've got 10 or more. So we just add up the 5% and the 5% and the 1% and the 1%, and we get 12%. So again, super straightforward. Part of why I think a problem like this is helpful to do is a lot of what we're going to do on this problem is really not very hard. But students just they make a question like this over complicated. There's an ATM question like this that you could practice with. And is on my older version of the Super 6 if you wanted to practice this some more. But I graded the ATM question, and it was just a bummer to watch students miss simple questions like this one. Part B, so part B, what's the probability? Calculate the probability that a randomly selected bath fizzy contains $100 given that it contains at least $10. So you see the word given there, and that means you've got a conditional probability. And so if we know we're in at least 10, which is the 12% that we just calculated, hint, 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 AP probability questions almost always build on each other. Notice on the last problem, we calculated that 0.62%, and then we used it later in the problem in the binomial part. Same thing here. You calculated a 12% probability of being 10 or more. Now you're saying, if you know you're 10 or more, what's the probability you're in the $100 prize? And so it's 1% out of 12%. which comes out to 8.3%. Again, you can ask challenging conditional probability questions, but this isn't one of them, right? It's really just, okay, we're 10 or more, take those 4 probabilities and then take the 1% out of the 10 or more. The trick is to remember that this isn't that hard. That's really the trick of it. And then finally, part C, expected value. As I said, as soon as we see this table, we're really smelling expected value. It's just what we like to do with this problem. And so we multiply and add, multiply and add, multiply and add. There's a fancier way to do this on your calculator, which we'll get to later in the problem. But frankly, if all you need is expected value, just multiply and add, multiply and add, and add them up. This formula is on your formula sheet, which you could find that to help you remember. But then we also had to interpret it in context. And so the $4.68 is the long run average when this is repeated over and over again. You could go read the rubric on this. You needed context. I think you needed context, mean, in the long run, 2 out of those 3 things is, I think, was what was required if memory serves. But you want to communicate this idea that an average is the long run average. Never round expected value. That's going to cost you points for sure. Does anyone win $4.68? Nope. I'm not saying someone's going to win that. I'm saying in the long run, this is how much is going to get paid out on average. All right. Your GPA is maybe a 3.8. Did you get a 3.8 in any class? Nope, it's your average. So we don't round averages. All right, and then the last part, this is kind of a funky little question. They basically asked you to convert this to euros. And we're told that $1 equals 0.89 euros. And so the fast way to do this problem is just to multiply 0.89 times the expected value and convert that to euros. Now, some of my students did this problem the slow way. They multiplied each of the original data into euros and changed the $1 to 0.89 euros and so on, and did that for the whole table, and then recalculated the whole expected value in euros, in which case they just got this answer the long, slow way. We talked last video about what I call the Ant-Man rule, that when you multiply your data times a scalar, you're just multiplying everything by that value, so you don't need to do all that work. You don't have to redo it. And fans of math will notice, if we go back to the last slide and you just multiply 0.89 times everything in that sum, well, you can multiply it times each part of the sum, or you can distribute it out, right? And so it's just a distributive property in practice. So, okay. The unfortunate thing that I think some students did is they divided by 0.89 instead of divided. And maybe you want to use a ratio here. Maybe you want to say, okay, $1 over 0.89 euros equals $4.68 over X euros, and then cross multiply. And that might help you make sure you did it right. All right. That was the end of the original question. It had 4 parts, part D. And now here come the extra parts to cover all sorts of fun probability questions. This first question, I don't see this being an AP question, but just a little reminder, problems like this are mutually exclusive and discrete. The variable can only take on one of 6 different values, and it can't take on more than one value at a time. Binomial problems are mutually exclusive and discrete. Geometric problems are. Normal problems are continuous. So just a reminder about those words. They're in the AP Stats guide, teaching curriculum guide. I don't know that we've seen them a lot. So mutually exclusive for sure, but discrete and continuous, not so much. All right. So now you're going to buy 3 prizes. And so what's the probability that you get that 68% smallest prize 3 times in a row? So this would just be the multiplication principle. And we just multiply the probabilities. What's the probability you don't receive a prize of more than $1 until your 7th purchase? And when you see until, I hope you're smelling the geometric distribution. We have 6 failures and then finally a success, 6 of the small prize. And then finally on the 7th try, the more valuable prize. So there's a 2.2% chance that you have to wait until your 7th try.
So when I do this with my students, because they have such a hard time with geometric probability, I have a cowbell. And so what I do is I say to them, this is college, so they're only a year or so away from you. It's not that much different. And I say, you do this, you go fail, 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 success. And I ring the cowbell. And so there's only one success. And as soon as you get there, you're done.
Nice, nice. I like it. I have cowbells behind me for the Redlands Bike Classic, which is a very fun event. And you ring cowbells when the riders go by. It's very fun. They're little, but anyway, I like it. Ring a cowbell when you win. Um, then at least one. And at least one is something that hopefully you've done a bunch of times by now. At least one success. And the mnemonic device that I always give my students for that is at least one is 1 minus none. Now you could do this problem in a binomial way, but it's harder work. Just do the opposite of getting at least one good prize is getting none of the good prizes and just all the $1 prize 5 times in a row. You could think of that as a binomial and having 0 successes and then doing 1 minus 0 successes. But again, that's more work than you want to do. Point 0.68 to the 5th power is the fast way to do 0 successes. And in class, you probably built up the binomial distribution and you did, I can easily calculate no successes. I can easily calculate all successes, and it's the ones in between that are hard and that we need the binomial formula for. All right. And speaking of binomial, here we've got, we're going to buy 10 fizzies and we're going to count the number of times we win a prize that is more than $5, more than $1. What are the mean and the standard deviation of this variable? And so what kind of variable are we talking about? Well, we're doing 10 things and we're counting the number of successes. That sounds like a binomial thing to me. And me and DeAnna's good buddy, Doug, one time said, in calculus, it's really easy to know what to do, and the hard thing is to do it. In stats, the hard thing is to know what to do. Once you know what to do, it's not very hard to do it. And this is a really, really classic example of that. Because once you figure out it's binomial, your formula sheet has a whole section that says, hey, here's the binomial formula for the mean. Here's the standard deviation for the binomial. And there's the mean and standard deviation for a binomial distribution. Once you figure out that part of the formula sheet is what applies to this problem, couldn't be easier. But yeah, but reading the problem, and it doesn't have the word binomial in there anywhere. So the next problem, similar flavor. If you buy fizzies until you win a prize more than $1, which apparently then results in the ringing of a cowbell. This is not something I knew. What are the mean and standard deviation of this distribution? So again, we have the word until, and so we're smelling a geometric distribution. So then we're looking at the geometric distribution section of the formula sheet. This really is new for those of us who have been around AP Stats for a while. The geometric standard deviation formula especially is new to AP Stats land as of 2019. And then of course we had the weird year in 2020. So anyway. And frankly, we don't see these formulas, these last two slides, this slide and the previous slide on the AP exam very much. But they're there and they're on our formula sheet. And the goal of the Super 6 is to give you a little bit of everything. So here it is. It's always fun for us to try and predict what's on the AP test, and then I don't get it right. But all right. Question I, a friend of yours buys the Bath Fizzies 5 times and only wins a $1 prize, and wins the $1 prize every time. He insists that the game is rigged. Explain why your friend is incorrect according to the law of large numbers. So according to the law of large numbers, the observed probabilities will match the theoretical probabilities in the long run. And again, this is an intuitive idea that you've had, in the back of your head for a long time now, but now you can explain it. So in the short run, it's not surprising that if in the short run that you observe less likely events. So in the short run, sure, this could happen. If your friend goes out and buys 100, then this is not very likely to happen. All right. Now, standard deviation of a random variable. So let's talk about that for a minute. This is something that definitely has been on the AP exam, I think only once ever on an FRQ that I can think of. Super infrequent. The formula for this is kind of messy. We've got this mean, and your formula sheet has a formula that looks like that. For the standard deviation of a random variable. And so if you wanted to show work, you would show some work like this. I recommend writing 2 terms when you write a dot, dot, dot. I need to remind my own students about this because sometimes I think they get a little lazy about this, but this is basically a weighted average, right? And now the standard deviation is weighted. So how far is 1 away from the mean times its probability? How far away is 5 away from the mean times its probability? And we're squaring these things because that's how standard deviations work. Squared things have nice mathematical properties of all sorts, and we get that value. Now, reminder, you can have your calculator crank this out if you put the probabilities as a frequency list. So for most of you, this would look like putting 1, 5, 10, 20, 50, and 100 into list 1, and then putting the probabilities, 68%, 28%, and so on, into list 2, and then running your 1var stats command, and then telling your calculator, my data is in list 1, and the frequency of that data is in list 2. And you will get the mean, and you'll get the mean, the expected value, out of your calculator and the standard deviation. Conveniently, the standard deviation will be labeled sigma. Inconveniently, the expected value will be labeled x bar, which you should never call it the expected value x bar because it's a theoretical long run expected average. It's not a statistic. So if it were me on the AP test, I would have my calculator get me the right answer, and then I'd write down a couple terms to the formula to show that I know what the heck my calculator did. And likewise, we did a bunch of binomial problems, and I forgot to mention, you can certainly show work on binomial problems by showing the binomial formula. I frankly wouldn't take test time to do that on an FRQ. I would just clearly communicate what's going on. The name, binomial, n equals, p equals, and here's the parts of the binomial probabilities that came out of my calculator. You have a good chance of seeing the binomial formula on an MCQ, but I don't know that it's a great use of time on an FRQ. Takes a minute to write. The binomial formula rubrics are very similar to the normal. Just the name of the distribution, the parameters, and then what parts are you working with? So are you doing the probability of exactly two successes, two or more successes? Just communicate what the heck you're doing. All right. And here's a good phrase. The typical distance of a prize amount from the mean is 11.57. That's a really big standard deviation. It's bigger than the mean, but that's the way gambling games go. That way you have lots of variability, and it makes it more fun for the gambler. Um, so, by the way, you could take that phrase, the typical distance of the data from the mean, you could apply that to every standard deviation you calculate in this class. We just did a mean and a standard deviation for binomial and geometric. So the typical distance of the, et cetera, et cetera. You can use this phrase for every mean and standard deviation. All right, we are getting to the end here. What if you bought 3 fizzies? And by the way, this is the more typical AP question where it gives you the mean and standard deviation. It doesn't ask you to calculate the standard deviation. And then it says, okay, what's the mean if I repeat this 3 times? Add up 3 means. What's the standard deviation if I repeat this 3 times? And here I'm going to pause. What do we do with the standard deviations in this case? The Pythagorean theorem of statistics. We square them and add them and square root them. Standard deviations don't add, variances add. So I need to square them and add them and square root them. And we'll hit this again in a minute, but reminder, you can only use the Pythagorean theorem of statistics if your observations are independent. All right, so now we're introducing another random variable into the party. And again, we're given the mean and standard deviation right up front. We have a new mean and we have a new standard deviation for Christmas time, variable y. So now we're going to buy 1 from each distribution. What's the mean and standard deviation of the total? So we have 2 means, 2 standard deviations, and we're doing the total for both random variables. So means are just nice and simple and just follow along with whatever rule we've got. Linear transformations, combinations, they just follow along. Standard deviations, not so fast. We're going to do the Pythagorean theorem again. We're going to square them, add them, square root them. So we're going to get a standard deviation of $26.19. And reminder, we can only use this when the events are independent. Cannot add standard deviations. We can only add variances. And then finally, we are getting to the finish line here. What's the difference of the payout? How much bigger is the Christmas payout than the regular payout? So now we're subtracting the random variables. And again, means subtract $2.81 more on average for the Christmas. And standard deviations still add. And I don't think we'll take time right here, but I hope you got a nice kind of plausibility argument from your teacher about why when you subtract two random variables, you still add the standard deviations. So we get exactly the same standard deviation as we had on the last problem. All right. Bonus question here, throwing in an inference question that's not in the Super 6. Suppose you bought 100 bath fizzies to test and see if this distribution works out. And you got 78 of the $1 prize, 12 of the $5 prize, and so on. What inference procedure would you run to test this company's claim? All right. I hope you were thinking chi-squared goodness of fit. We have counts in one category and a distribution that would be expected to fit. You put those counts into list one in your calculator. You'd multiply 100 times the probabilities and you get 68 and 20 and so on. Put that in list two, run goodness of fit. Goodness of fit does not show up very much on the FRQs. It's quick and fast to run, so it's been in some MCQs historically. It's a fun little test to run. I kind of feel like we're due for chi-squared as maybe the inference question, but now I'm really going out. DeAnna's face says no, but
No, I just was thinking about we had a practice AP exam on Saturday, and I wanted to have you address how important it is to name a test to name a chi-squared test appropriately. That you can't just say it's a chi-squared test.
yep.
You need to say it's a chi-squared goodness of fit. So, like, is it that are the days of the week or births on the days of the week evenly distributed, or
Mm,
do my individual categories match some uh, published percentage? That's goodness of fit. But then there's the other two, which is a chi-squared test of independence. In that
mhm,
case, what you have is the key there is you start with one group and you look at two different labels that you put on every subject, in which case we're wanting to know, are these two labels independent of one another? Is there an association? Sorry. And so
Yep.
that's a chi-square
Or
test of
independence. Yeah.
independence. Yeah,
Yep.
and then the other thing is like if you have separate groups taken, so you have separate populations from which you've taken a sample from each, and then you want to see if there's a variable that's distributed the same across those individual populations, then that's a chi-squared test of homogeneity, homo meaning same, so same across. And we no longer can give you partial credit if you just say chi-square. You have to say chi-squared what? Chi-squared test of goodness of association or independence, chi-squared test of homogeneity, or chi-squared goodness of fit. And that's, I think, going to be a challenge in the future of AP statistics is that
Well, they did require that on the multi-focus question 2 years ago, either 2 or 3 years ago. There was a question about soft drinking soft drinks in three different cities, Detroit, San Diego, and I don't remember the third. And they didn't run, students didn't run the full inference procedure, but they were asked to name it and to write the hypotheses. And then they had to name a chi-squared of homogeneity. And the problem said at the very top that they collected three independent random samples. And so the students were super clearly told at the beginning that it was saying three independent random samples. Well, then that tells you straight up, this is homogeneity, not independence. Now, you still have to remember that, but I did at least the stem was very clear. So
yeah.
the problem with some of the problems in our textbook is you can't tell how many sample if it's one random sample and two variables or if it's multiple random samples. And that's where sometimes our books are just, they're not the AP exam and they're not that high stakes. And I know for stats modeling the world, a lot of times we want the problems to be realistic, which makes for good discussion, maybe not the best AP exam questions. And I think that's okay. But all right. Any last questions?
So we have a question from an anonymous student for six letter K. Would there be any scenario would you multiply the standard deviation instead of squaring, adding, and then square rooting? And so not in AP statistics, we don't multiply variance or standard deviations together for any reason in this
Yeah,
level of statistics.
no, not at this level. I mean, if you have if you're doing data conversion, the way we converted the data to euros, the standard deviation gets multiplied by that same factor. So you can multiply a constant times the standard deviation, but not at this level. We're not going to do a product of any standard deviations. So. All right. Well, why don't you go ahead and stop the recording? I think, Deanna, I think we're good.
Okay.
Mm.
I was just answering, so wanted
Oh, yeah,
to.
you're good.